So we want to define limits. So before we define limits, we have to first fix a category I, which is a kind of an index set. And limit is defined on a functor. Yeah, this is important to notice. The limit is defined on a functor. So what does this functor do? This functor actually acts on an index category and it lands in the category C. So although limit is defined on a functor, it is essentially an object in the category C. Yeah, this will become clear later on. We have fixed I to be a small category so that it has its objects as sets. So this F takes ij to ci to cj. Now the way to remember this is consider I as a partially ordered set. So that is not exactly correct, but that is the way to think about it, or that is the way I like to think about it. So I consider I as a partially ordered set, and in that way you have the morphisms. So this is how we write the limit. So limit is always of a functor, but in terms of thinking, you should think of it as an object of category C, and this F here, which takes an index set to a category C, is called the diagram indexed by I. So F is called the diagram indexed by I. So although F is a functor, it is called a diagram indexed by I, and when we talk of a limit of a functor, we essentially mean an object in the category C. Now why are we writing it so complicated? Just think of it as category I is just inclusion of sets and C is some functions on it or some associated cohomology groups on it. So yeah, this is what you have to keep in mind. So what does the properties of this limit object? So there is a morphism for each j in I. So if you have some j, you have a morphism to cj in category C from this limit, and there is a corresponding commutative diagram. If you have an arrow like this in category I, then you have this commutative triangle in category C. So I am interchangeably writing limit ci underscore I with limit f. Yeah, this is just to remind you that limit is of a functor, but it is an object of the category. So yeah, this thing commutes. We just write some name the morphisms. Again, we can write if there is another object x which has exactly the same properties. Notice that we are using precisely the ideas of products here, and this will be clear in a minute. Then there exists a unique morphism G which takes x to this limit. Now as a result of this definition, this unique morphism G means that limit exists uniquely up to isomorphism. Yeah, you can draw a reverse arrow from lim f to x and then identities and then show unique up to unique isomorphism. So limits are also known as projective limits, or they're also called as projective limits and sometimes as inverse limits. So much for what the definition of a limit is. But now I want to make an important remark. The way to understand or write limits is this. Yeah, you take the collection of objects in the category Ci. So when you're thinking of a limit, you should think of the category in which the functor f lands. So category C. So you have, this is a collection of objects in the category C such that we have Fm acting on Cj gives you Ck. This is precisely what is there in the commutative diagram I have drawn. For all k, for all m in the index category, which have an arrow from j to k. Yeah, so this is it. It's a collection of objects, and you have to think of it in terms of a product. So, and these maps fj and fi, you can think of them as projections. So let us, what are the consequences of such a thing? So consider this functor f from IOP to set, and then you fix an object x of set. So set a object or fix a object x of set. Then you define another functor again from IOP to set. It will take I, this will get mapped to, yeah, so the underlying set here, the objects are morphisms. Now this, why are we writing like this? We want to make this important remark which essentially validates why we are writing the star. So what is the important remark? So if you just factor the product out, just think of it in terms of homomorphisms. So instead of direct limit, you write product. This is what you will get. You get the direct limit outside, that is, you get the product outside. Yeah, now we are thinking in terms of star. You get set fi inside. Yeah, you're taking this limit. I'm saying direct limit. This is not direct limit, this is inverse limit. So what does this mean? So now we are defining the this projective limit or limit. So this limit on the right hand side, this is nothing but a collection of maps. Yeah, so if it is a direct product, you can think of it as a huge collection of maps, x to fi. But each of this map filters through our object of the category C. I should say factors through. Factors uniquely through. Yeah, this you can again see in the diagram. This G is the unique factor. So yeah, that is pretty much it. So now we start discussing the examples for limits. We have already done two examples. First is products and second is pullbacks. So let me write this down. So first example we have discussed is of products, and then we followed it by pullbacks. And the third example which I want to talk about is p-adic integers. So p-adic integers, you write it like this. So we will denote p-adic integers by z, p and they are written like this: a0 plus a1p plus a2p square, and so on, where each of this ai, the a0, a1, a2, a3 and so on, each of this lies between 0 and p. Yeah, it's an integer which lies between 0 and p. So obviously if we take this term and modulo it pq, what will be left is a0, a1p, a2p square. Then you can again modulo it p square. What will be remaining is a0 plus a1p. Then modulo it p. What remains is a0. So you can form these arrows. Modulo, keep on modulo it. Yeah. So similarly, the ZP, the entire series, you can form arrows like this, and you have this standard modulo. It will commute. So for example, for p cube, you will get a0, a1p, a2p square, and for z modulo p square, you have a0 plus a1p. So if you want to write ZP as a product, like a series like this, then you can think of the above series as this. Yeah, as a product like this. So colimits are somehow more useful. So you just reverse the arrows in the definition of limits, you get colimits. So let us write this down. Colimits are also called direct limits and injective limit. So this should remind you of the direct limit which we use in algebraic geometry or in sheaves. So just reverse arrows in the definition of limit and we get colimit. Now colimit is denoted by this. Notice that arrow has reversed. We will reverse the arrow as we had compared to what we had written before. So this is what you get in the category says C. Again, it is unique up to unique isomorphism. Let me write this down. It is unique up to unique isomorphism, and just like with analogy with before, just for the sake of completion, let us complete the figure. So we have Cj here, say Ci here, we have a map Cj here, then we have an arrow here. Again, all arrows have been reversed. We'll write this as Fi, Fj, say Fm here, and m goes from I to j. Notice that arrow goes from Cj to Ci, but here we go from I to j, m. So Fm goes there. So yeah, basically arrows have been reversed. Everything else is the same. So this arrow I to m, I to j with morphism m, this is in category I. Now examples, the first examples you would have guessed by now. Coproduct and pushouts. Then the third example is that this is again analogous to p-adic numbers. Yeah, so this is nothing but all rational numbers with denominators as powers of 7. You could be taking any prime number actually here. It's a power of 7. So again you have the map, say just the integers, then 7 inverse c, that is denominators just consisting of 7, denominators 7 minus 2, yeah, and so on. So you have these natural maps. Yeah, so all maps are inclusion maps here. So on this slide, we want to talk about a filtered category. So we start with the definition of a filtered set. So you start with the partially ordered set, say S with this relation greater or equal to. Now this set is called filtered if for each x comma y in this set S. So let us write this down. For each x comma y, so there are two elements x and y in the set S, then there is another element z such that x is greater or equal to z and y is greater or equal to z. So we will copy this definition to a filtered category. So first note that filtered category is non-empty. So a category I which is non-empty is filtered if for two objects x and y in category I, there is an object z in category I and morphisms or arrows. So instead of greater or equal to sign, we just write morphisms. So there are two morphisms like this. So this is the first condition, and we have a second condition. So let me write this down more clearly. First condition, and then we have a second condition. So when there are two arrows from x to y, one is u, another is v, and then you have an arrow w which takes y to z. Yeah, so that is pretty much it. Yeah, so if there are two arrows from x to y, then there is an arrow w from y to z such that you first apply u and then apply w is same as first applying v and then applying w. So we want to talk about colimit of f. A functor f which takes, say, acts on this filtered category I and it takes it to set. So we want to talk about colimit of that. So in order to do so, we have to first define an equivalence relation of something like this fi, where I is part of the filtered category. So this we have already done before, like in some sense in limits. So you have this disjoint union. Yeah. So how do we define this relationship? So you have fi and fj, you fix an element x and y in fi and fj. So then there exists this k and as an object of the filtered category, such that if you have a diagram like this in I, so this is a diagram in the filtered category I, then analogous to what we had in limits, you have something like this. This is in the target category. So I'm saying you're going from I to set. Target category is set. So in set, you will have this. You have just applied functor f. So what is the equivalence relationship? So equivalence relationship has to be defined between x and y. So the equivalence relationship is nothing but an equality here. So fs acting on x is equal to, you guessed it, ft acting on y. So you can see this R is an equivalence relationship. So you can just draw arrows and see the definition of equivalence relationships and just start drawing arrows. So instead of greater or equal to, you just start drawing arrows. And that is this. R is an equivalence relationship But this is what we want to show. We want to show that this direct limit or co-limit, this is what we wanted to show for the functor f, which takes a filtered category to set, is nothing but this disjoint union, which I had written before, disjoint union, modulo the equivalence relationship we just mentioned above. So we start to prove the result which we mentioned at the bottom of the last slide. So we're given a functor f from filtered category to set. We want to show that direct limit can be given this as disjoint union modulo certain relationship which we defined on the previous slide. Okay, so let us show this. So you start with here, you say direct limit of f comma s, where s is the fixed object of set s. So now you can say, since you have fixed this object s, you're putting this here, you have to take care of arrows. This is a contravariant functor, so the arrows are not going to go in the direction which you expect them to go. So what is this? This is nothing but just this set of maps fi to s, where I is the element of the index category. So this is what it is. This is just from the definition. And if there exists an arrow like this in category I, we have the following diagram. Notice again the direction of arrows is not what you expect it to be. The definition we had fj to fi, but here we have fi to fj, precisely because this direct limit is coming as a first factor. So you have this following commutative diagram, and we will show that in essence this commutative diagram itself implies the above relationship. So in order to show that, we define another map, in fact another term, say pix, where p you can say stands for projection. Yeah, so we want to define something like this. So what is this? This is I belongs to the index category and x belongs to the fi. Yeah, that is, it belongs to set, because fi obviously lands in set. And then we have this equivalence relationship. So where does this equivalence relationship come from? We obviously want to identify the above triangle, commutative triangle here. So we just start copying stuff. So there has to exist I to j s, and now we have to connect this thing. So fi with fi to fj, but now we will do our equivalence relationship, that is x here in fi gets mapped to y here in fj. So this is the equivalence relationship which we mentioned on the previous slide, and this is precisely equivalent to what we have in this triangle here. Yeah, so you are identifying x with y. X in fi is identified with y in fj. Yeah, so we have done nothing much. So you can again go back to the first diagram and say that commutative triangle fi to fj fs and then ui uj is equal to identifying x in fi and y in fj. So what is this equal to? This p I comma x modulo the relationship pix equal to pij. This is nothing but this disjoint union of all these fi's. Yeah, you have all these x's, they're disjoint union, and disjoint union you know is written as I comma the set, and you see the first factor is like this. So we are done. You just need to know how a disjoint union is written. So now we want to record an important example of localization. So in fact we can say we just talked about these filtered categories, etc., because we wanted to construct localization. So in fact, that's how the development of category theory has been. You first have important concepts and then you just try to rewrite them. So localization is a colimit over a filtered set. So you are given a filtered set S, and localization is nothing but a colimit. The beauty is that it will even make sense when you localize a set A, or which is not an integral domain. So let us write what I have just said. Localization is a colimit over a filtered set S. Now S is multiplicatively closed, so you write it like this. Yeah, this is again important in algebraic geometry. You take open sets and you define localization on those sets. So S is multiplicatively closed, and this will make sense even when A is not an integral domain.